Welcome back to Let's Code. I'm Chris Biscardi, and today we're going to talk a little bit about Netlify serverless functions and what my preferred approach for both building, shipping, and running them is. Now, this is even an issue because of... So to start off, on the right-hand side here, we've got a serverless function that I've called. I can hit it, enter again. You can see the response come back again. It's the same thing. On the left-hand side here, we have some logs from that function. We can see that the first execution of this function took 1.3 milliseconds. The second one took 0.85 milliseconds. It uses about 16 megabytes of memory, and the cold start is 30 milliseconds. So these are pretty good numbers as far as serverless functions go, especially if you're used to JavaScript cold start times and execution times and things like that. Now, the issue isn't with the running of the functions. These are just regular functions. I didn't do anything special to them. They are the size that they would be if you just cargo built them by default. They are shipped to Netlify manually, which is important, and then they can run. It's wonderful. The reason I was working on the functions and the dependency updates and the build system is that you can see here in the build, I'm running cargo zig build and targeting a specific version of glibc. Netlify functions run on AWS Lambda, which uses Amazon Linux 2 under the hood. And notably, any Rust program that you create, well, not any of them, but by default, most of them are going to rely on glibc, which is a shared libc library that exists on whatever target system that you're going to run on. So it's kind of the only thing that you have to have installed on your system for a Rust program to be able to run that you compiled somewhere else. Now, there are other libcs that we'll talk about in a second, but fundamentally, the glibc version that you are running on the target system, so in this case, our Netlify function, has to match what you compiled for, more or less. So Amazon Linux 2 has glibc 2.26. And the big problem, if we just kind of let Netlify build this for us, is that the Netlify CI environment doesn't necessarily have glibc 2.26. It may have something newer like 2.3.0 or 2.3.1 or something like that. Which means that our Rust application, if we naively compile it on CI in Netlify with just using cargo build, we might get a Netlify function that doesn't run, it doesn't work, because it's trying to call a glibc function that doesn't exist in the glibc on Amazon Linux 2. Now, there is a solution to this. There are a couple solutions, actually. One of the big solutions to this is to compile with a different libc. It seems to reason that if we have a trouble targeting a specific version of glibc, that if we don't use glibc, then we don't have trouble targeting a version of it. And muscle libc is a libc that is meant to be compiled statically and included in your program. So the weird shared library-ness of glibc goes away if we use muscle for our Rust libraries. And this is what Netlify has chosen to do by default in their experimental Rust build support. So if you ship Rust code in a functions directory to Netlify and let them take care of building it, they're going to build it against muscle. Now, the big problem with compiling with muscle is that a widely used cryptography library called Ring doesn't support cross-compiling with muscle libc. This is really unfortunate because libraries like Request, which are the first result that people often see when they Google for how to make an HTTP request with Rust, Request uses Ring under the hood. So if you get somebody set up with a Rust serverless function on Netlify functions and you've cross-compiled with muscle libc, and strictly speaking, they are a new Rust developer, a new Rustation that doesn't really know what cross-compiling means, has never really heard of libc before, and doesn't know what muscle is, they are going to run into weird runtime errors that they are not going to be able to fix. So if I, as somebody who teaches Rust and teaches serverless Rust specifically, tell somebody to use Netlify's support for muscle to build their serverless functions, it will work for them for the workshop or the video or whatever. It will also probably work for them for a little bit longer, depending on what they're trying to do. Now, when it won't work for them is when they go to make a request to an API, or if they use maybe something like their SQL library depends on Ring, that will cause build failures for them. And the build failures that you get when you're cross-compiling with Muscle are not user-friendly. They are not something that I would want a beginner to run into without supervision, basically. Now, it's fine. Many people can get past this and kind of figure out how to get it to build and whatnot, but it's a very frustrating issue. So what I've decided to do instead is that for all of the things that I teach, I am not going to use Netlify's CI environment for Rust serverless functions. What I'm going to do is I'm going to tell people to use Cargo Zig build. And now Cargo Zig build will let us not only target the version of Linux that we need to target Amazon Linux 2, it will let us specify glibc 2.26 as our target, which completely gets rid of all incompatibility issues unless you compile anything on crates.io as you would normally. Now, this, I think, is the preferred solution. I hope that at some point Netlify switches from using Muscle to using Cargo Zig build by default. That would solve so many issues in this case. Until they don't, one of the things that I've updated the Netlify examples repo in the Rust Adventure GitHub org with is the ability to use Cargo Zig build. Or more accurately, the only solution I suggest is using Cargo Zig build. Now, this is unfortunate because installing Cargo Zig build on Netlify would require this like super alpha support of something that isn't really suggested. And that's using a brew file to install not just Cargo Zig build, but Zig the language, in addition to doing your build manually with Cargo Zig build. And the errors here aren't, again, fun to debug or fun to work through. So I've chosen to not recommend this as well, because not only is it not fun to work through, but it is not, as far as I know, stable and officially supported, although it does technically, or you can get it to work. It does include quite a bit of extra time at the beginning of your build to download these additional dependencies, when I think they could just be installed by default. So you'll see here that I'm suggesting using Cargo Zig build, which means that either you're building your Rust functions locally on your own computer, or if you've taken to the more modern practice of using CI systems like Netlify CI or whatnot, you can use GitHub Actions to build these functions and then send them to Netlify. And you can use GitHub Actions caching and things like that, which are things that I dive deeper into on Rust Adventure. So if you're interested in that, go check out Rust Adventure. I'm in the process of rewriting the Netlify Serverless Functions workshop to use Cargo Zig build and GitHub Actions instead of the Netlify CI. So that'll have all the information that I'm going over right now. Now, that all said, upgrading the dependencies is still interesting, right? So we've got a way to build any crate that we want to, package it into a binary, and then we ship the binary to Netlify and everything's good. I still want to go over the upgrades that I made to Lambda Runtime and AWS Lambda Events. Lambda Runtime is at 0.5.1 for the latest right now, and Lambda Events is 0.6.3. The Lambda Runtime is the thing that lets us actually run serverless functions in Rust. It is the runtime that handles, we'll talk about this in a second, but it's the runtime that handles our execution of the function, the receiving of the events, and the execution of them. And then AWS Lambda Events is basically a package of structs and types that allow us to deserialize from whatever's coming in into a specific type. In this case, it's going to be an AWS gateway type, and then also have a type for the response that we're returning from our function. So if we look at the hello world here, I'm bringing in a couple things from Lambda Events. I'm bringing in a header map from HTTP, and I'm bringing in stuff from Lambda Runtime. We've got two functions, one of which is a main function and one of which is a handler function. Our main function contains all of the code that is going to run when our function first boots up on cold start for the very first time. Anything that we need to do for initialization will be in here. For example, we could connect to the AWS SDK to DynamoDB and keep that client around between serverless function invocations or something like that. And then the handler is the thing that runs every time an event comes in. So in this case, we upgraded to using this Lambda event with a type argument of API Gateway Proxy Request. And the API Gateway Proxy Request is the AWS type that includes all the headers and things like that for Netlify functions. If you use AWS Lambda yourself, there are a number of different types that you can use depending on what kind of setup you have. If you're using, for example, a Lambda proxy or an HTTP API or a REST API, even AppSync has its own types for resolvers, and then DynamoDB Streams has another. So all of those are in the AWS Lambda events crate, which is wonderful because we just get to use them and we don't have to write them out ourselves. And in the handler, which receives every event, so an event comes in, we get this Lambda event, and then we have to return a result type with an API gateway proxy response. And the API gateway proxy response has a status code, any headers that we're including. They separate out regular headers and headers that can have multiple values into two different fields here. And then we have the body and whether it's base64 encoded. This is the same object that you would send back if you had a JavaScript Netlify function. It's just explicitly typed out here. So in this case, we send back a body of text that is just hello Rust. And on the right-hand side, you can see this function with all the crabs that says hello Rust. Now, if you're unfamiliar with what's going on here at all, basically Tokio main is an async runtime. The way that async works in Rust is not quite like other languages. The syntax support and some of the other support is in Rust's standard library, but the actual runtime itself is one of a few different third-party crates, the most popular being Tokio. So in this case, we actually can't have an async main function, and this attribute macro from Tokio will rewrite this main function to bootstrap its runtime and then call our main function. Super useful macro. Tokio is a great project. And then we call this run function from the Lambda runtime. And that takes our function and basically turns it into a handler that the Lambda function runtime can then repeatedly call with events as it comes in. And under the hood, this is implemented as a stream, if I remember correctly. I'm not going to talk about streams today. I talk about streams in the Rust Adventure workshops if you're interested in that. And then basically for this run, we await it. And if anything goes wrong, then we return the error from this function. Otherwise, we do okay. Basically what this does is it will just like stay here forever. So it's not actually something we run and then pass through. It's something that we run and then we'll just stay there forever. And what AWS does for our functions is it will run our function. It will give us an event. Our handler will get run. And then before anything else happens, it will sort of like hibernate our function. So the stream that we define internally inside of the Lambda runtime to handle the stream of events that are coming in will get basically frozen and then given one more event, and then frozen and then given one more event, which will cause the handler to be the only thing that runs every time the serverless function boots up. So all told, I think that some of the changes that have gone through in the Lambda runtime maybe make this a little bit more verbose. There used to be like a attribute macro here that we could do like Lambda runtime function. I forget what it was called, but it was basically an attribute macro like this. And then we could get rid of the main function, which does make it a little bit nicer, a little bit smaller, but they got rid of the attribute macro. So now we have to write out the actual cold start, which is fine. It's not that much code. And it allows me to talk about the cold start versus the warm execution and what's actually happening. Now that's hello world. We also have a number of other examples here. We've got calculator, JSON response, query string, redirect. In this case, we've got query string. I'll just drop query string in here and say, I think it's name equals Chris, and I'll get hello Chris. If I don't include the query string, I should say hello stranger. And we should see a couple of logs come in here, about 2 milliseconds and 1 millisecond, 16 meg memory usage, 17, init duration for the cold start, 32 milliseconds. So these are pretty average numbers. And if we open up the query string example, we can see that there's a very similar function happening here. In this case, we actually use the event. So that was one of the changes in the Lambda runtime API. We now need to use this Lambda event, and the context comes from calling into parts on that event. This event is the new event, the inner event. This is the API gateway proxy request, in which case we say in the query string parameters of the API gateway proxy request, grab the first value that has name. So in our case, it's the query string value name. We only have one of them. So we get, if there's one defined, we get it. If not, then we don't. It's theoretically, you could send like multiple query string parameters with the same name. So that's why it's called first and not just like get or something like that. And then we use unwrap or. So this is an optional type right here. And then we format this value, whether it exists or not. If it exists, then it's the name. If not, then it's stranger. And we format that into a string. And then we do the same response. So API gateway proxy response, and we send body text with the response. So overall, the upgrades aren't too bad for the actual functions. I did want to cover the additional build approach that I've taken to recommending to people. It's not the only approach, but I think that cargo zig build is overall the right way to do this. So we'll take cargo zig build, we'll target exactly the glibc that we want. This gives us all of the access that we could ever want to any of the crates.io crates that we want to use without having to worry about, hey, we recommended that you cross-compile, but some things don't cross-compile. Now, we're still cross-compiling. Don't get me wrong. We're cross-compiling from Mac to, or in this case, from Mac to Linux with a glibc 226, but we are not cross-compiling using muscle libc, which is the big hang-up. And of course, that just puts the binary in target Linux release hello world or whatever. We dump those binaries into functions, and then we ship it to Netlify. Now, we do have other functions here. One of them is request dad joke. So if we go to request dad joke and go to request dad joke and I grab it and we paste and go, we will get, I've deleted the phone numbers of all of the Germans I know from my mobile phone. Now it's Hans free. And we can see that the runtimes for this function are a little bit longer. The initialization duration is not any bigger than it really was before. We use a little bit more memory because we're making an actual API request to a dad joke API. And the actual duration is 60 milliseconds because we actually do have to make that request and get a response. So that's Netlify serverless functions and my suggested approach to building them. I hope that this helps you if you are intending to deploy serverless functions to really any AWS-based platform. So this includes Netlify, AWS Lambda, etc. You can take the same approach. I suggest cargo zig build for AWS Lambda directly as well. I think it gives a lot more flexibility than going with muscle. And if you're a beginner, it is much more understandable. It's kind of easier to say, hey, we're compiling for Linux against this glibc. It's a lot harder to explain, hey, we're compiling with this other glibc, but also it might break some stuff. So good luck. Happy serverlessing. Happy serverlessing.